As we begin lesson 7.4 on logarithms for Math 30-2, I take a minute to look at these two review questions and see what you remember about how to simplify question 1 and then isolate the x in question 2. Now, we haven't talked about solving, but just think about what you know switching between exponential and logarithmic form. All right, pause the video now and do the two questions. So here you have my first step for question number 1, where this 2 that was in front of the logarithm, I needed to bring that into the exponent before I could combine the logarithms together. And now that I have that in the exponent, I can combine these together. So again, as we looked at in our previous lesson, since this is a positive logarithm, and then we have an addition sign in front of that third logarithm, I can combine those two together and say I'll have the log base 5. And again, when we're adding those logarithms, that means we're multiplying the powers, and the a squared is the power, and the c cubed is also the power. And then for this middle term, since we're subtracting that logarithm, then that means we'll divide the power, which is a b. So there we have log base 5 of a squared c cubed all over b. So a little bit messy, but there you have the idea. Now, as we look at question number 2, you'll remember that if I want to switch from exponential to logarithmic form, I will start with my logarithm and say that I have a log base 7. Because my power was base 7, my logarithm will be base 7. I remember that a logarithm is an exponent, so this is equal to x. And a logarithm operates on a power, and this 7 to the exponent x is a power. That's equal to 80, so 80 is my power. So there we have the question solved. We may be asked to evaluate this, in which case we would want to get out our calculators. And if you figured out how to evaluate logarithms in different bases, you can type it in just like this. Otherwise, if your calculator can't work in different bases, then we can rewrite this as the log base 10 of 80. And remember, if we don't write a base in, that means it's a base 10, a common logarithm, divided by the log base 10 of 7. And so that is what we would plug into our calculators. And if we want an answer to the nearest tenth, this would be approximately 2.25. If we wanted an exact value answer, then we would just say there's our answer. If we want a decimal approximation, we'd say that is our answer. Okay, and that's where we're going in today's lesson as we look at solving exponential equations using logarithms. First, some warm-up questions. So again, I'll have you pause the video and complete these 4 warm-up questions, it looks like. Maybe just before you do that. Again, our measure of success today is just being able to use logarithms to solve exponential equations. So fairly straightforward. Okay, pause the video and do these warm-up questions, please. So here you see question 1 is complete, and hopefully you came up with an x value of -4. If you didn't, pause the video, take a few minutes to look through my process. As we look at question number 2, there's an interesting step that we need to do at the start. Because we have two y's, but they're a common factor, what we want to do is factor that out as a common factor, as I've shown in that line that I've written. And then I have our 1 minus x that's multiplied to that y. So that 1 minus x, I can divide on both sides of the equation. Now we're asked to solve in terms of y. I should say solve for y in terms of x. And so we're going to have an x in our answer. And here this 1 minus x and that 1 minus x cancel out, which leaves us with our final answer that y is equal to 2 over 1 minus x. And that would be our answer for question number 2. Question number 3, similar to our warm-up question. As we rewrite this, my base is 3, logarithm is an exponent, and I'm taking the logarithm of the power. So again, I've solved an equation, which is what question 4 is getting us to. Well, a different method for solving an equation. So we're asked to take the common logarithm of both sides. So I'll do the log base 10 of 12 on the left, and I'll do the log base 10 of 3 to the exponent x on the right. Now, here, what we're wanting to do is solve the equation for x. So we want to get this x out of the exponent. So we remember the exponent laws from the previous lesson where we can take that exponent and multiply it down in front. So this right-hand side will be x times the log of 3, and the left-hand side still the log of 12. Now to isolate the x, we can divide both sides by this log of 3. Which tells us that the log of 12 divided by the log of 3 is equal to x. So again, we have a solution. And take a look here at the answer to question 4 compared to the answer of question 3. The two questions were the same, 12 equals 3 to the exponent x, but our answers look different. Even though the answers look different, they must be the same value. So our answer for question 3 will be log base 3 of 12. Our answer for question 4 is the log of 12 divided by the log of 3. Since these are both solutions to the same equation, these two must equal each other, which is the change of base rule that I mentioned in the warm-up or in the review questions before the warm-up. Now, just before we formalize this change of base rule, if we wanted this answer in decimal form, we could plug it in either. If we can do log base 3 on our calculator, we can plug it in and get an approximate answer of 2.262. If we can't enter log base 3, then we can evaluate it by rewriting it as the log of 12 divided by the log of 3. And if we plug that into our calculator, we'll also get 2.262. Now, let's formalize this change of base formula. So here we have it. Log base b of x will equal the log of x divided by the log of b. So you'll notice that the base for a logarithm becomes the argument of the logarithm in the denominator. Now here I rewrote it as a common logarithm because that's the most useful form for this change of base rule. But we could actually do this with any base. We could say the log base a of x over the log base a of b. So I could choose a base of 3. Like in the previous question, we had a log base 3. So if this was log base b of x here and we wanted to evaluate it, I could do log base 3 of x divided by log base 3 of b. As long as those two bases are the same value, then we can use this change of base rule. Another one that we could use with our calculators is doing a natural logarithm. So I could do the natural logarithm of x over the natural logarithm of b. So again, you'll remember that ln button on your calculator takes the natural logarithm, which is a log base e. Log base e of x over log base e of b. And again, because these two bases are the same, the change of base rule works. But again, as I mentioned before, key idea is this one at the start here, and most of the time if we want to use the change of base rule, we'll change it to a common logarithm. And that's what we're asked to do in question number 5 next. We want to rewrite this as a log base 10. So we'll just say this will be the log of 100 divided by the log of 2. Then we're asked to evaluate to 3 decimal places, and here on the right-hand side, I've written that answer. So this is approximately equal to 6.644. Let's move on. As we look at this example, we looked at questions like this in chapter 6, so let's just do a bit of review as we get into this question. First, reading the question, Ella Jade has a balance of $3,625 in her savings account. Well, before I go any further, looking at that formula, we have an A value, remember that's a future amount. We have a P value or principal, that's the initial amount. That's what we're given so far in the question, $3,625. Then we have an I, remember that's the interest rate per compounding period, N, which is a number of compounding periods. Okay, let's continue reading the question. The account pays 2.2% interest per year, and it's compounded annually. So every compounding period is a full year. And so my interest rate is 2.2%. I want that in decimal form, so 0.022. A represents the future value. That summary is in this sentence here. We want to know how long it's going to take for Ella's balance to reach $5,000. So that's our future amount of $5,000. We want to know how long it will take, so we want to solve for this n value. Now in chapter 6, the only way we could solve for this typically was by graphing. But now we can use logarithms to solve this. So let's fill in the values into the equation. Our future amount equals our initial amount times, remember, we have the 1 here because this is 100% of her initial amount of money we're going to keep, and we're going to add on that 2.2% n times. So in this next line, I'm going to do a couple things. I'm going to combine these two values into one, which gives me 1.022 to the exponent n. But I'm also going to take this 3,625 and divide it to the other side of the equation. So I'll have 5,000 divided by 3625. Well, if I do 5,000 divided by 3625, I'm going to get a long decimal number. And I don't want to use rounded values in my calculations, so I could store that in memory for future calculations, or I can just leave this as a fraction. So for now, I'm going to leave it as a fraction. But I've got to a point where I have a number equal to a power. So I can rewrite this in logarithmic form. So again, I'm going to rewrite it as log. My base for my power is 1.022. My logarithm is an exponent, so this is equal to n. And this is operating on, well, let me get a little bit of space here. I know it's going to equal n, but let me first stick in 5,000 divided by 3625, and that will equal n. So again, if your calculator can work in a base other than base 10, you can plug this in just as it is, or I can use the change of base rule to say that my n value will be the log of 5,000 divided by 3625 all over the log of 1.022. Either way, as you can see, we are going to get an answer of 14.8 years. As we look back at the question, we were asked to approximate the solution to the nearest tenth of a year. So there's the nearest tenth. So I didn't worry about rounding up or down based on the information of the question. I went with the instructions that said just to the nearest tenth. Okay, so I didn't have to worry about, oh, should I be rounding down? In which case, actually, it's not going to reach the amount of 5,000 in time. So do I actually have to round up? So don't have to worry about that given the wording of this question. Okay, let's move on to question number 7. In question number 7, we have Sean working at a laboratory that uses radioactive substances. So we did talk a little bit about half-lives in chapter 6. So this will be a half-life question again. So here we're looking at radioactive radon 222, and the laboratory received a shipment of 5,000 grams. Only 13 grams of the radon remained 19 days later. So given the formula we have there, and we'll typically be given a formula for a question like this, let me list out the information that I have. A will be my future amount, and my future amount is 13 grams. A sub 0, the initial amount, we started out with 5,000 grams. The base we're given in the question. T is how much time passes, and H, remember, is the half-life. And again, half-life is talking about how much time will pass for the substance to decay to half the original. So let's come back to the question. We know how much is left 19 days later. So is this 13 grams here half of 5,000? I mean 500? Nope, it's not half. So this 19 days isn't a half-life. That's just the amount of time that has passed. Now notice here, as we saw in chapter 6, these two A values have the same unit. They're both grams. And so this time and the half-life, those will have the same units as well. So we want to solve for what the half-life is. So let's set up our equation. Our future amount, 13 grams, is equal to our initial, 500, times a half to the exponent 19 over h. That 19 is a little bit hard to read. Let me just rewrite that. This will be a 19 over h. So as we did in the previous question, we want to start by dividing the 500 out on both sides of the equation. So we have 13 500ths. This time that fraction would turn out to be a relatively nice decimal, so feel free to convert that to a decimal if you like. And our variable is in the exponent. Even though we have a 19 in the exponent as well, still at this point we can rewrite this equation in logarithmic form. Well, there you see the answer already. It's given away. I have a feeling I'm going to run out of space, so I'm going to come over here to write this in logarithmic form. A logarithm, my base is a half. This is equal to the power, which is 19 over h. And the logarithm is being taken, oh, it's equal to an exponent. My mistake there. It's equal to the power, which is 13 over 500. So here I still want to solve for h. Again, I could plug the logarithm into my calculator at this point, but I'm going to leave it as an expression for the moment. And what I'll do is I'm going to take this h, which is in the denominator, I'm going to multiply it up to the other side of the equation. Well, I'm multiplying it on both sides of the equation, actually. So I'm going to multiply h on the left and the right. Here the h's cancel out. And then, because I want to get h by itself, I'm going to divide both sides by the log base 1/2 of 13 over 500. So a few things happened there with my limited space. I've combined some steps together. So here, now this logarithm cancels out. So my left side is just h. My right side is 19 divided by the log base 1/2 of 13 over 500. And that's an expression that I can plug into my calculator. And when I plug it in, what I should be getting is about 3.6. And so that's what we have in our answer here. Again, feel free to pause, look back over any of these examples that you still have questions with. And then when you're ready, we can move ahead. And here's a check your understanding question that, oh, I've given the answer away too, but pause the video at this point and try the question. So here I've set up the equation. This time, what we're trying to figure out is a time. We already know the half-life. That's what we figured out in the previous question. Now, usually we'll want to keep more decimal places just to be a little bit more precise. So if I wanted to do that, then this should be a 0, 8, 5, and a bunch more decimal places that we could keep stored in the calculator. As we solve from here, again, we'll start by dividing both sides by that 500. And this time, because it's easy for me to do in my head, I'm going to change this to a decimal, 0.2. That'll be a half exponent t over 3.6 with all the decimal places. Rewriting this in logarithmic form, I have a log base 1/2 equal to the exponent t over 3.6 with all the decimal places of 0.2, which is what the logarithm is operating on. Now this time, a little bit simpler because I want to solve for what's in the denominator. So I can just multiply, I should say what's in the numerator. I can get rid of that denominator, multiplying both sides by 3.6. On the right, they'll cancel out. And on the left, I will get t is equal to 8.38. Well, notice this answer here is different than the answer that I have written down there. Why do you think that might be? Pause the question, think about it, and then when you're ready with an explanation, we'll restart the recording. Well, if you guessed that this is based on the rounded value for the half-life, then you'd be right. So those decimal places make a difference, especially in a question like this. So if you're not told, as in this question we weren't told, do I use the rounded value? Do I use the non-rounded value? Typically we would say keep all the decimal places to the very end. But because we did have a question part earlier where we calculated that amount, if you had used that rounded value in your calculations for question 8, I would give you full marks. But as a general practice, we should be using the non-rounded amount. Okay, let's look ahead at some more examples. So now we're not looking at a question in context, but we're looking at just playing with numbers more or less. So a little bit more complicated because this time in our exponent we have an expression for x. But we saw this before in the half-life question where we had the variable in the denominator initially and then in the numerator for question number 8. Our steps will be the same. So we will begin by rewriting this in logarithmic form. Because I have a power equal to a number, I can jump right to that and say log base 3 of 20 will equal my exponent, x minus 1. And then it's just a matter of getting the x by itself as I add 1 to both sides of the equation. But here we need to be careful. So we have log base 3 of 20 plus 1 is equal to x. This is a correct answer. If I had taken this 20 and added the 1 to it, it would not be a correct answer because the 1 is added to the logarithm base 3 of 20. It's not simply added to the 20. So let's back up and write this a little more correctly. Oh, went too far. There's a bit of a delay. So if I wanted to be super precise in what I'm writing here, I could put brackets around that log base 3 of 20. It doesn't have to be there, but for some of us that may help us to be a little bit more careful, making sure that we don't make the mistake of adding the 20 plus the 1. Now for this question, we were asked to round our answer to 3 decimal places. If we wanted an exact value answer, this is what we would leave. So this would be an exact value solution. But rounding to 3 decimal places, this is what we would do, and we'd get x is approximately equal to 3.727. Question number 10. Similar idea, but a question where a few more of us will make a mistake. You can already see the answer in decimal form there, but let's rewrite this again in logarithmic form. My base is 2. Log base 2 of 6 is equal to 1 minus x. Now here, this subtraction sign on the right side sometimes throws people off, but notice that this is a positive 1. So to get rid of that positive 1, I need to subtract 1 on both sides of the equation. When I subtract that 1, the right-hand side will still have a negative x because the negative is part of the coefficient of the x. And my left-hand side will be the log base 2 of 6 minus the 1. Again, I can't do the 6 minus 1 because the 1 is not simply subtracted from the 6. It is subtracted from the log base 2 of 6. So let me add in some brackets there. Finally, I want to figure out what positive x is equal to, so I'm going to divide both sides by negative 1. You get the same result if you multiply both sides by negative 1. That just changes the signs on both sides. So I'll have x is equal to the negative of log base 2 of 6 plus 1. Or we could say that x is equal to 1 minus the log base 2 of 6. Again, this would be our exact value answer. If you're ever asked for an exact answer, it'll be an expression with logarithms, typically. If you're asked for an approximate answer, that's where we put it into decimal form and we round appropriately. All right, Ready for some check your understanding questions. So look ahead at question number 11. There's the answer already. Once you have worked through the question and you want to see my solution, then restart the video. But for now, I'd say you should pause it while you do your work. There you can see my process. Now notice this time I did something a little bit differently, where when I subtracted both sides by 2, instead of subtracting it behind the logarithm, I decided to add the -2 in front of the logarithm. Either way is perfectly fine, and really it's just a matter of what you would rather do. For this question, I was kind of thinking ahead, recognizing that I was going to be dividing by -1, which would change my signs. And so I just liked how this answer would look, rather than doing the negative log base 5 of 104 plus the 2 afterwards. Here's the answer we should get when we plug it into our calculators to get an approximate decimal value. So, how are you doing with solving exponential equations? This ends this lesson. Take some time to work through the practice questions, and then we will move on to our next lesson, which looks at modeling data using logarithmic functions. So that will be using logarithmic regression, just like we've used regressions for linear functions, for quadratics, for cubics, for sinusoidal functions, and for exponential functions. All right, I'll see you in the next video.